Okay, let's dive right into this. Today, we're tackling something you've absolutely seen if you're working through the Cambridge AS and A-Level Physics 9702 syllabus. I'm talking about radioactive decay, and more specifically, that unavoidable exponential decay equation, x equals x0e to the negative lambda t. Now, whether x represents the activity of a sample, the count rate, or the actual number of undecayed nuclei, this single equation is going to come up constantly. It is literally unavoidable in the examination series. But, looking through the source materials and the examiner reports, it's pretty clear that this is also a massive opportunity for you. So beyond just plugging numbers into the math, there's a highly specific strategy to navigating this, and that is exactly what we're going to unpack today. Here is our quick roadmap for the explainer. We'll look at the challenge, dive into the core principles, map out the procedural framework, review some direct examiner warnings, and finally wrap up with those top mark strategies. Part 1, the challenge. So why do so many students find multi-stage analysis and actually securing those method marks so incredibly hard? Well, picture this. You flip to a multi-part question on your exam and boom, you're hit with a massive wall of text, a bunch of complex data, and an intimidating exponential equation. It brings up a really critical question, right? Because it's usually not that you don't know the formula. The real obstacle, it's the cognitive overload of trying to interpret raw data, remember all your physics principles, and format it all perfectly while the clock is ticking down. Part 2, core principles. The absolute best way to beat that cognitive overload is to completely strip away the intimidation factor. Look, the equation x equals x0e to the negative lambda t isn't just a basic algebra test, it is a meticulously designed assessment tool. According to the syllabus framework, this formula actually targets 3 distinct cognitive domains. First up is knowledge and understanding, meaning do you know what the decay constant lambda actually represents? Second is application. Can you manipulate the equation to find the half-life? And third, systematic analysis. Can you draw evidence-based reasoning from a physical decay curve? The whole theoretical architecture here rests on precise definitions. If you truly understand the physics behind the variables, the math just becomes a tool to express it. Now, what's really fascinating here is the insight straight from the grading room. This is pure insider knowledge. This quote is pulled directly from the principal examiner reports. Candidates referencing cross-topic connections achieve significantly higher marks. See, radioactive decay doesn't just exist in a vacuum. The documentation clearly shows that linking this equation to other areas of your syllabus is the secret key to unlocking those higher grade brackets. For example, linking how the energy released during decay connects to mass defect, or how the properties of alpha, beta, or gamma radiation connect to electric and magnetic fields. Doing that signals to the examiner that you have a master-level grasp of the subject. Part 3, the procedural framework. To consistently secure those elusive method marks, we need to move from abstract concepts to a rock-solid, repeatable process. The materials outline a highly effective 5-step deconstruct, solve, evaluate methodology for tackling literally any radioactive decay problem. Step 1, deconstruct the question. Find out exactly what they are asking for. Step 2, extract relevant data from the texts and tables provided. Step 3, select your analytical framework. You have to decide, do you need the exponential decay equation right away, or do you need to calculate the decay constant first? Step 4, execute systematically using super clear notation. And step 5, check for reasonableness. I mean, if you're calculating a half-life of 3 seconds for uranium-238, that is a huge red flag that something went wrong in your math. And here is where we hit a really important realization. Marks are awarded for the process, not just the final answer. This is the method mark strategy in a nutshell. Think about it. If a simple calculator typo messes up your final number on step 4, but your extracted data is clear, your analytical framework is written down, and you used proper terminology, you're still going to secure the vast majority of the marks for that question. Executing with clear notation, like explicitly defining what x represents in your specific calculation, is honestly just as crucial as double underlining your final answer. Part 4, examiner warnings. Okay, so even if you know the right way to do things, what are the common traps? Looking directly at the principal examiner's notes, 3 classic pitfalls emerge that constantly cost mathematically capable students top grades. First, answers are often just way too vague. The reports heavily stress the need for specific, precise physical details. Second, students completely forget about format and presentation conventions. The framework demands strict adherence to proper headings, correct terminology, appropriate units, and clear annotation. And finally, the third big mistake is that answers are simply not specific to the context given. Let's look at the difference between a generic answer and a context-specific one, because this is huge. The ultimate examiner alert is when they read an answer that correctly defines exponential decay, but entirely ignores the actual scenario of the specific isotope mentioned in the prompt. If the problem is talking about carbon-14 in an ancient archaeological sample, your analysis must reference the activity of carbon-14, not just say the sample. The golden rule found in all these reports is to always link your analysis, your variables, and your final justification back to the specific physical problem right there on the page. Part 5. Top mark strategies. So, how do we push an answer from just good to exceptional? It all comes down to evaluative thinking. The data shows that candidates hitting those higher-order assessment objectives don't just calculate, they evaluate. This means actively questioning the assumptions of the model, for instance, pointing out if background radiation hasn't been accounted for. It means considering different perspectives and evaluating alternatives, like maybe discussing the limitations of using a Geiger-Müller tube for a specific type of measurement. Above all, it involves justifying your decisions with solid evidence. Making justified recommendations based on a calculated decay rate is what proves to the examiner you have a true, deep understanding of the physics. Now, trying to keep all of this procedural stuff in your head under the stress of an exam can be tough, but a great memory hack suggested in the source material is to use a visual story method to encode these concepts. Try picturing a literal story for the equation. Imagine x0 as a giant towering pile of unstable blocks, lambda as a ticking metronome dictating the pace of the collapse, and t as a calendar rapidly flipping its pages. Visualizing the procedural framework, deconstruct, extract, select, execute, check, as a physical journey makes recalling these technical steps so much faster when your time is running short. Which brings us to a final, pretty provocative thought. When you sit down to tackle your next past paper, are you just blindly plugging away at a calculator? Or are you truly evaluating the decay process within its specific context? Remember, mastering this isn't just about getting the math right, it's about proving your entire methodology. Think about that next time you practice. Thanks for joining me on this explainer, and I'll see you next time.